AI didn't just get smarter, it got better at looking trustworthy. That sounds minor. It is not. Modern tech runs on signals. We outsource judgment to metrics, benchmarks, demos, repo stars, leaderboards, trending charts, launch clips. Those signals tell investors what matters. They tell developers what to trust. They shape hiring before products stabilize, funding before usage is clear, what gets copied next, and what gets buried. So when the signal gets corrupted, the entire ecosystem bends with it. That is the real AI trust crisis. Not bad models, bad measurement. And bad measurement is dangerous because it looks objective from a distance. You see a score, you relax. You see momentum, you assume merit. But once money starts following a metric, the metric stops being innocent. It becomes a target. Targets get optimized, sometimes honestly, sometimes strategically, sometimes theatrically. Let's trace exactly where trust breaks and why it keeps breaking. Start with something deceptively simple: the GitHub star. GitHub says stars help people discover similar projects. It also says many repository rankings depend on star counts, and that Explore surfaces popular repositories based on those counts. Which means a star is no longer a passive bookmark. It is distribution. It is social proof with algorithmic leverage. A star changes who notices you. A star changes who copies you. And because it changes attention, it changes opportunity. That is why this matters far beyond ego. A paper on fake star campaigns makes it explicit. Star counts are widely used popularity signals, and they can be artificially inflated, reducing their value as decision-making signals. The same paper ties inflated stars directly to supply chain choices. Developers don't just admire high star projects. They adopt them, depend on them, bet systems on them. Now add fraud to that picture. Suddenly, discovery becomes an attack surface. The paper identified more than 4.5 million suspected fake stars across 15,135 repositories. Not a funny edge case, a measurable shadow market. And it accelerated hard in 2024, the part most people missed. At the July 2024 peak, 15.8% of repositories with 50 or more stars had fake star campaigns detected in that single month. Think about what that implies. Discovery itself can be gamed at scale. Not perfectly, not forever, but long enough to distort attention. And temporary distortion is often enough. It only needs to open the first door. There is also a price tag on this, which makes the incentives painfully obvious. Dagster bought fake stars to study how the market worked. They found 1,000 fake GitHub stars selling for as little as $64. One vendor delivered 100 stars to a dummy repo in 48 hours. That is how cheap synthetic credibility gets once a metric becomes valuable. Here is the logic that scales this beyond stars. If a signal affects discovery, people will try to buy discovery. If it affects funding, people will try to buy funding optics. If it filters technical choices, people will try to buy perceived legitimacy. Not real legitimacy, but perceived legitimacy at the right moment. Perceived legitimacy is often enough to get compared seriously, enough to trend, enough to enter architecture discussions, enough to get one influential engineer to give the thing a chance. Then real attention arrives. The fake signal has done its job. Corrupted metrics don't need perfect deception. They only need temporary belief, long enough for momentum to compound. And once momentum compounds, people start calling it validation. The tokens change, the pattern doesn't. Benchmarks were supposed to discipline hype. They were supposed to ask the hard question: can the model actually do the task? But benchmarks have a fatal vulnerability. Models can see the exam. A report on open contamination says it plainly. Data contamination lets models cheat through memorization rather than generalization, creating an illusion of progress, distorting comparisons, and undermining benchmark integrity. That is not a critique of one model. That is an attack on the scoreboard itself. And once the scoreboard is suspect, every improvement carries a question. Did the model learn, or did it remember? The report measured contamination levels ranging from 1% to 45.8% across benchmarks. A huge range, but even the low end matters. Benchmark rankings at the frontier often shift on tiny percentage differences. Tiny leaks can flip narratives, and contamination grows rapidly over time. The longer a test circulates online, the harder it is to read cleanly. Examples spread in forums. Solutions spread in repos. Mirrors spread everywhere. Eventually, the benchmark stops feeling like an exam. It feels archival. That is why saturated tests produce so much false confidence. We see a model ace something familiar and mentally upgrade its real capability. But a contaminated benchmark may not be measuring reasoning. It may be measuring exposure, formatting familiarity, retrieval luck. Can detection tools save us? That would be comforting. Comfort is the wrong expectation. A 2025 paper on reasoning model evaluation shows why this gets nastier. Leaderboards turned evaluation into a competitive arena. Competitive arenas create pressure to optimize for the visible score. The shortcut is straightforward. Use benchmark data to raise benchmark scores. Then enjoy inflated performance and cleaner leaderboard narratives. Once rankings become prestige infrastructure, they become manipulation targets, not always with malicious intent. Sometimes just with competitive desperation. Then the paper says something genuinely chilling. Evading detection is alarmingly easy. Even worse, the paper studied how reasoning model training changes the evidence. Brief reinforcement learning training can conceal the contamination signals that most existing detectors were explicitly relying on. The model looks cleaner after the optimization stage. The cleaning smoke drifts in the same direction as progress. In one scenario the paper examined, most detection methods performed near random guesses on the specific task of spotting benchmark contamination. Near random. That is how trust fails twice. Inflation happens. Then the safety net weakens. The score keeps looking impressive. The collapse stays invisible.
Bard will become more visual.
Claude identified the build errors and is now fixing them.
Our most intelligent AI experience.
People usually blame demos. I want to be careful here. Not every demo is fraudulent. The deeper problem is selection. Public attention sees the best path, the cleanest prompt, the most flattering environment, the nicest clip. What you almost never see is variance under pressure. How often it fails, how sensitive it is to wording, how much scaffolding surrounds it, how narrow the success path actually is. That hidden variance is everything. It is the difference between demo and deployment. A benchmark hides variance. A launch video hides variance. A viral thread hides variance. A leaderboard definitely hides variance. Trust dies in the gap between what can happen and what usually happens. One of the clearest illustrations of this gap comes from game evaluation research. The LM Game Bench paper asked a deceptively simple question. How well do LLMs perform when dropped into games? The answer was not amazing, it depends heavily. The paper identified 3 reasons direct evaluation fails: brittle vision perception, prompt sensitivity, and potential data contamination. And it says direct placement often performs poorly, sometimes close to random action baselines. That should immediately reset expectations, because public conversations usually present the strongest example as the system itself. The strongest example is often the system plus a wrapper. Perception modules, memory modules, reflection, prompt standardization. The model is not acting alone. Wrappers change apparent capability enormously. The same paper quantifies this directly. Without harnesses, 40% of game runs fail to beat random. With harnessing, 86.7% of runs beat the random baseline. That is not proof of dishonesty. It is proof that context matters. And when context matters that much, single numbers become dangerous summaries. This carries directly into production. Wrappers are everywhere: retrieval layers, tool calls, routers, guardrails, validators, human escalation. The right question is no longer, can the model do one impressive thing? The real question is, under what conditions does it keep working? That sounds less glamorous. It is also much closer to the truth, because reliability compounds brutally across multi-step AI workflows. One slightly flaky retrieval, one slightly flaky tool call, one slightly flaky synthesis step. Suddenly, the whole chain feels unreliable. Pretty good does not automatically become trustworthy, especially when the cost of being wrong lands on users, not on the benchmark. Now, we reach the most practical layer: fabrication under document grounding. This is where many companies expect RAG or long context to save them. Give the model the documents. Reduce hallucination. The promise sounds reasonable. Sometimes it works. But measurement still matters. A 2026 document Q&A study tested 35 open-weight models across multiple context lengths and settings. It's finding even the best-performing models still fabricate answers at non-trivial rates. Best case at 32K context, 1.19% fabrication. For top-tier models, fabrication often sat in the 5 to 7% range. That sounds small until the workflow becomes high stakes. A few percent error in casual chat feels annoying. A few percent error in legal review, medical search, or contract extraction feels costly. Then context length expands, and the reliability story worsens. The paper reports that fabrication nearly triples at 128K context. At 200K context, every model exceeded a 10% fabrication rate. Long context is not magic. Stuffing more text into the window does not automatically produce trust. The model still needs grounding discipline and fabrication resistance, and the study says those are distinct capabilities. A model can retrieve facts well and still invent facts it never saw. This is exactly why flashy demos mislead. They compress away the failure distribution. You see the one successful path. You do not see calibration quality. You do not see how often the system drifts under longer contexts. You do not see how often the wrapper rescued the answer. You definitely do not see what the benchmark accidentally taught it. Capabilities are rising. That part is real. But the interpretation layer around capability is warping under incentives. Investors want one clean metric. Media wants one clean ranking. Audiences want one clean answer. Which model wins right now? The market rewards that simplification. Reality does not. Reality gives you distributions, edge cases, domain shifts, brittle chains. Reality asks whether the system holds up on a boring Tuesday, not whether it produced an incredible launch clip last week. That is why this is a trust crisis more than a capability crisis. Raw models improve. The interpretation system degrades. And when interpretation degrades, capital flows toward the wrong things. Engineers copy the wrong practices. Teams benchmark the wrong outcomes. Users inherit the wrong expectations. Then disappointment gets blamed on AI itself. But often the deeper failure is not raw intelligence. It is poor epistemic hygiene, weak measurement culture. And once weak measurement culture spreads, it normalizes benchmark theater, selective demos, and popularity masquerading as quality. That is why the ecosystem feels confusing. Everything is legible, yet little feels solid. You can always find a screenshot, a chart, a leaderboard, a viral thread. An honest reliability envelope is much harder to find. Not a single benchmark. Never one number alone. Trust bundles of evidence, especially evidence that disagrees. Use clean evals and adversarial evals together. Use public variants, not just best case examples. Ask how sensitive the system is to prompt wording and data format. Ask how much scaffolding is required to reach the headline result. Ask how performance degrades as context grows longer and messier. Ask whether adoption matches attention, because attention is cheap to manufacture. Ask whether reproducibility survives outside the author's ideal environment. Ask whether the benchmark has a contamination story at all. Ask whether the detector would still work after optimization stages. Ask whether the team shows failure cases, not just hero examples. If they do not, assume the variance is larger than advertised. Because real trust is not look what this can do once. Real trust is here is where it fails and why. Real trust is provenance, clean separation between training and testing. Real trust is honest reporting about scaffolds, tools, and wrappers. Real trust is knowing what the number does not say. That is harder to market. It is also what serious teams actually need. The next decade of AI will not be decided by demos alone. It will be decided by which systems survive contact with reality, which companies can separate signal from theater, which builders can resist metric worship, which researchers can design evaluations that stay meaningful under pressure, which users learn to read scores with skepticism instead of awe. The core question is not, is AI getting better? The core question is, can we still measure improvement honestly? If that answer drifts toward no, the ecosystem gets noisier, not wiser. More launches, more charts, more rankings, less clarity about actual reliability. And every new breakthrough becomes harder to trust. That is the cost of a corrupted measurement system. Not just confusion, misallocated attention, mispriced confidence. So yes, be excited about progress. Some of it is absolutely real, but stay suspicious of clean narratives, especially when the stakes are rising. Because the future of AI depends less on peak intelligence and more on whether measurement stays honest.